So, for our next talk, we will explore how Linux is used for space missions. An extraordinary talk, actually. Please, Sal, the stage is all yours. Let's give her an applause.
All right. Oh, wow, we can now. Hello. All right. Hello, everyone. I am Sal. If you have seen one of my many talks before, surprise, we are not talking about cybersecurity or the supply chain or any of that today. We are talking about space because I wanted to. So this talk is by me this time, and I am representing Gadfly AI. That is the group that I run and work with. We do take on contracts. We work on a combination of cybersecurity and SRE enhancement. I cannot currently take any more clients at this time, nor do we have a marketing budget, as you will see if you look at our website. What we do instead is have a maintainer budget. And I invite maintainers to come and talk about really interesting security issues. So just about 2 weeks ago or so, one of our maintainers from Gadfly gave a very interesting talk about how to design the minimal Linux kernel to be able to rickroll your friend's hardware without allowing any other potential security vulnerabilities. That is the kind of stuff we work on. I encourage you to check it out. So this is what we're going to learn today. I'm going to tell you a little bit about the history of space, the Linux kernel, and then, as promised, the kernel in space. I am looking at space not because I have clients in that area, but because very specifically I find it one of the most interesting places to think about designing for resilient software and hardware. So we're going to talk about error detection, fault tolerance, communication protocols, and then we're going to talk a little bit more about what it means to have initiatives like this. How is something like space exploration influencing the way that we are designing something like the Linux kernel? This is a pretty good time to warn you that you may experience some forms of motion sickness along this talk. Almost every single one of these slides has a video in it because I thought that would be fun. If you find otherwise, let me know, and I will change my slides for another talk. But before we go to the moon, I want to clarify just exactly what it is that we're talking about if we're talking about open source. It's not a business model. It is a very, very good way of sharing what I would call intellectual property or lines of code in which you make statements about how you want to maintain that code. You hand it off freely to an individual, and they can reuse it for their own purposes as long as they retain that ability to keep that open in the style that you license it as. This has become incredibly critical, and if you are watching this on a recording, I would encourage you to look up Open Source Day UNICEF and look at some of their constraints around open source, for example. Now, there's a difference between the Linux kernel and the Linux Foundation. So the Linux kernel is something that you are all pretty familiar with. The Linux Foundation is much broader. It really functions over every form of technology that we are encountering that sits on top of the Linux kernel. I myself have done a bunch of security slams and interventions inside of CNCF, the Cloud Native Computing Foundation. I've also worked with OpenSSF, which is their Open Security Foundation. I'm now currently working with one of my favorite clients, which is the Confidential Computing Consortium, in which we are working now on designing completely secure, completely encrypted on the way in, completely encrypted during runtime compute, and completely encrypted on the way out, secure systems. And my last statement, I like to focus around the Linux kernel and to communicate to people how working with the Linux kernel might feel a little bit different from other forms of open source as we think of it broadly. In this situation, we're often constraining the way that we build open source to things that are ISVs. These are institutions that have a sort of higher standard of regulatory pressure on them. And so a lot of those function and work around when they need software development and open source around the Linux Foundation, because it gives you a couple of guarantees. It gives you vendor independence. It ensures that even if a company or a maintainer is unable to maintain their service, that you will have someone step into place. It allows you to have really high-functioning, sustainable open source, and I like the direction that a lot of our work is going in that space. And so, with that brief introduction, it's time to explore space. So So this is space exploration according to Sal. You will notice that is missing a couple of details, but according to me, this is what happened. In 1957, we sent the first Sputnik into space. After that, we started sending people to space, people to the moon. A lot else has happened since then, but I don't find any of it very personally interesting. I only get interested when chips get involved. So let's talk a little bit about what kind of chips might be engaged and what kind of software we're going to be engaging with. So the Linux kernel was established in 1991. It's now, I think, 31 or 32 years old as a main kernel. And it's still completely and entirely supported and has expanded since then. The kernel, the part of the kernel that I find really interesting right now is anything that's built over secure primitives. So we're really focusing on building kernels that have security as the total basic structure. And now, when did the kernel go to space? So it started really with NASA taking it on in the late 1990s, and since then it has been used in almost every single space mission, and it has been used by almost every single space industry, right? Coming back to the idea that they want to be using a software that is going to be compliant for them, that's going to last a long time, that they know that they're going to have the open source support around. And I think that this is driving some of the most interesting efforts towards resilience, sometimes security, but mostly the really good thought-provoking work around designing resilience is happening because of space exploration. So all of these participating agencies work with the Linux kernel: NASA, ESA, JAXA, ISRO, CNS, and DLR, and SpaceX. Where is the kernel living now? Right now, the kernel runs most of the operating systems that are on the ISS. It's on all of the Mars rovers missions, Spirit, Opportunity, and Curiosity. It is in any of our Earth observation satellites and the Hubble Space Scope. Almost everything is touched by the Linux kernel, but I think these are really interesting examples of things that still require international agreement, compliance, and operation. So how, then, in this little thought experiment, has space exploration changed the kernel? It's teaching us a couple of really, really interesting things about how to design software and hardware for very extreme environments. So it's teaching us how to resist radiation and how to build error systems that allow and account for that, redundant computing schemes that I find very, very interesting, and fault isolation techniques that we should probably be implementing widely, whether or not you're going to space. So what does this look like? So radiation is just a really nice way to sort of tell yourself that you're going to have high entropic instability in your systems. You might have random bit flips. What do you do if you're going to be encountering radiation-induced bit flips that have nothing to do with computation that you want to preserve? In this case, we're building really cool systems. So we've got ECC, so we've got error correction codes that are these memory controllers that essentially allow you to hold and track these sort of states of your system, and then a hardware watchdog timer that comes in, right? Like a beautiful little cron job that says, all right, we can go back to the last known state, to the last known bit flip that was induced by our computing system. And as we should be building in all these systems, we want to be checking the expected parity. This is just as important for a system that's going to be experiencing radiation as for a system that you would build on Earth if you want it to be lasting 10 times longer, and you want to be able to trust those computations over time. Now, redundant computing. I'm going to give you just a couple of examples that are commonly implemented in space design, but there's many more that I think are really critical, and it probably deserves its own white paper. But triple modular redundancy is one of the more traditional ways of doing this. The problem is that's hardware modulated. It means it requires 3 times as much hardware to be able to deal with the default. The dual modular redundancy system is just slightly more logic gate complex. But again, this allows you to be doing this a lot more efficiently, sometimes on the same board. That's really cool. Now, software-based redundancy is where the Linux kernel comes into this. So we are building kernel-level fault tolerance techniques. So this system allows you sometimes to duplicate the critical components and make sure that you can do sort of an operator jump over to what is running with best function and optimality. I find this space really interesting, and as we move into the potential of having higher powered chips in space, it's going to become only more important because we will be doing more IoT computing at the edge. And this is the real edge of space. So, fault detection, right? So, fault isolation techniques. This is really important. So we want to do strong memory protection mechanisms. This is a space that, again, we are being sort of motivated by these extreme edge cases where we need to send these entire objects out, and we can only do sort of like distal updates to the software. The hardware is what it is at that stage, right? So if you're building this way, you want to do memory protection mechanisms, process and address space isolation. I won't go into detail on this, but this is important. Kernel module isolation. Probably from this entire talk, if you build and design anything of a secure system or anything which requires privacy-enhancing considerations, the kernel module isolation is very, very important to understand. Increasingly, as we are building things out over hypervisors, as we are relying on other servers and other people's hardware to run our software, you always have to consider that you can containerize, you can constrain, you can secure, but potentially, if you can't completely attest to the hardware underneath, you could have something from a hardware or an operating system up vulnerability. So isolating is important at the kernel level. A few other things that space is helping us with, but that sort of open source broadly does not get to participate so much in because they're constrained, are the specialized hardware. So we are building out CDKs specifically for these space agencies, unified device models that make it really, really easy to start and build out entire algorithmic or computational objects. And again, this mainline kernel support is the reason why Linux is going to continue to go to space. And if you today want to go home, get on GitHub, and contribute something that will have an impact on space, all that you have to do is go and contribute to CubeStat. And one quick note on this, NASA, about 2 years ago, is doing its first wave of chip development, so putting out really, really high-performance chips into space. I keep looking for updates on this, but they decided to go with this microchip processor. I'm hoping this year we're going to see some of those first results. It's 100 times better compute than what they have out there. Communication protocols, I think this group will probably find these very boring, so I'll skip over it. But they're interestingly constrained to this space. So let's talk a little bit about what makes space exploration different as compared to a lot of open source, which considers only software. Hardware and software have radically different constraints. I did most of my career in software, jumped over to hardware, and discovered that because the real world requires real objects with real materials, we have to consider that. So, anytime that you're sourcing hardware, you got to deal with the constraints of COTS. So these are commercial off-the-shelf, right? This is exactly what you think it is. You want to be able to pick up a part, you want to be able to read what it says on the tin, and to guarantee that it works that way. It has to be maintained, it has to be interoperable, and it has to be cost-effective. This is constraining the kind of software design that we put on top of these systems. So, COTS in space exploration, obviously the microprocessors and microcontrollers, the communication systems and the power systems, and the sensors and actuators. Great. What does this mean when we're engaging with the Linux kernel? Where is it sitting in all of these? Well, Linux kernel is the thing that does the process management, memory application, everything for these microcontrollers and microprocessors. It is involved in the TCP and stack implementation, socket handling, web interface management of all of the communication systems for all of these services. And particularly in the power and sensors actuators, it's not in those systems itself, but anywhere where you see a sort of dashboard level or sensor aggregate level communication of those systems, that's also run on Linux. And for the fun part. So it's also, and this is where I became more aware of it, it's also been pushing the limits of what we do for cryptographic modules. So this is a secure primitive. And within this space, we've really focused on doing like really nice asymmetric encryption. We've got some great techniques going on there. Digital signatures, this is one of the first places to really pick that up. So if you're seeing that now in your like salsa S-bomb world, This is one of the first places where we needed to get that right. Secure communication, right? So again, this is coming to, can we fully encrypt a set of information that we're receiving from a satellite or from a space station all the way to Earth or to its intercept routes along the way, and can we ensure that both that transmission and every nodule of information where it hits hardware is also not compromised. And this comes down to data integrity and verification, right? So not only do I want to make sure that it was not gotten to, but I want to make sure that it was not gotten to and altered, which can have serious constraints if we're doing something like telemetry, if we're trying to receive telemetry around things like climate control, if we're pointing any satellites back to Earth, that kind of misinformation can be incredibly dangerous, and we are concerned about those kinds of intercepts and tampering. So intrusion detection systems have not been pushed so much by this space, but they've been radically utilized by it. So we obviously monitor the system activities, and the alerting and response in this space is sort of interesting. We do a lot of the traditional sort of network monitoring, scan it, see if there's anything abnormal, but you can also be looking at some aggregate sensor details and sort of asking the question, is there an erosion in the signal because of some solar event, some entropic event, some destabilization of the hardware, or is it in fact a cybersecurity incident? That becomes pretty challenging in space, and working on those aggregate and the signal processing techniques is invaluable. One of the things that I see all the time in this space is one of my favorite algorithms, which is dynamic time warping. It's a very efficient sort of two-columnar way to define whether or not this behavior of a specific system is compliant to the way that it has behaved on different sort of times or time scales. And remote confidential compute. So this one is a little bit theoretical and a little bit not. So right now, there's the ability to fully encrypt and bring data up and down from these signaling spaces. But what I think is much more important to consider now is making sure that the hardware that you are sending it to itself is secure. Increasingly, no individual country has control over the supply chain of chips. They never will. You cannot have a complete guarantee. But you can have, again, complete isolation of your kernel, complete isolation of your system, attesting the hardware, and making sure that when you compute, this is one of the biggest cybersecurity concerns that I'm seeing in 2024, and that's why I'm working with the Confidential Computing Consortium to get this word out. When you compute, typically you don't have the ability to keep sensitive data encrypted. You've had to traditionally decrypt it to get into compute. Confidential computing allows and preserves that. We are going to see a lot more instances of utilizing that and making sure that there is a complete hold down from where the information comes from in space, all the way back down, all the way back up. And as that continues to improve, you're seeing the effects of this also doing massive good in spaces like banking or spaces like genomics. Confidential computing is allowing you to do that kind of work. But again, it's going to be front and center in space exploration for the next 10 years. So a quick little note on where else the kernel is. It's the first time I've given this talk, and I will absolutely be expanding this section, also giving this with a couple of hardware maintainers who will get a really hard hardware look. But one of the things that I would love for everyone to pay attention to and just go look at, because I think it was really well designed, it's really interesting. So I used to work a lot with supercomputing, right? Trying to figure out in these kernel spaces, when are you building something that's really efficient? And so this kernel for hyperspectral imaging, this is something that you can go and play with. It's something that you can go contribute to right now. And so you can sort of work with the sort of data processing time if you're going to work with Whirlpool, or you can just contribute to this kernel. I find it really, really fascinating. So what is next in the wave of space tech? This is where I take all of your buzzwords and say, is it relevant to this talk? Let's start with AI and ML. So there is limited implementation of AI and ML in space, but let's talk about all of the issues that we discussed just before this, right? You've got a highly extreme environment. You're likely to experience radiation. Radiation affects your bit flips. If you're dealing with a highly entropic system, you may not want to be doing a massive amount of compute at that edge. You want to find a way to securely store that and get it back to a different compute space. They have traditionally been a little bit too power heavy. This is itself changing as well. There's also other ways to do hardware implementation. So if you've looked at photonic chips, for example, I'm interested in the feasibility of photonic chips in space, but they likely have additional constraints for that environment. And the real-time processing. This is a problem that I think people don't really consider unless you've actually built in this space. But let's talk about the probabilistic nature of most AI and ML. Let's talk about the very brief consideration that now you've got so much compute that a lot of people sometimes make stupid choices about compute. If I was to send something out into space or send something to do a investigation of sort of a military service or even a healthcare service, anywhere where you've got critical services, you can't use something like Boolean statistics. Boolean statistics, once you get to over about 100 nodes, you can send the exact same information through that network and you can get the answer yes and no, depending on what you send out to it. So there's just a couple of conditions where if you've got something stochastic, it's probably not something that you want to be putting out there anyway. Massive ways to compute, and you won't get a definite high veracity, capital V veracity answer. Quantum in space. So this is experimental. A lot of people have talked about this. Does it really exist? Not really. So quantum itself is still under development. Again, it's just probably is not the best kind of system to be sending to space. That doesn't mean that you can't be taking the telemetry data, bringing it back down, and doing that here. The cooling requirements also just do not work in this case. Again, maybe in 20 years we could be seeing that, and I'd be curious to see it. Let's talk about the thing everyone's most afraid of, quantum attacks. Is it going to get us? Honestly, probably not. We are pretty far away from quantum attacks being a regular thing, and you also have to look at the threat model of all of these objects. Who would be the adversary? Why are they motivated? And how strongly are they motivated? I just simply do not see quantum attacks being pointed at space, although they are going to be pointed at other Earthbound systems. So it could have an impact on space, but we're again looking at about a 15 or 20 year out potentiality, and by that point, we will have a much better threat model for it because they're going to hit Earthbound systems first. Now, I'm going to wrap up this talk just to sort of consider that the biggest problem we probably have is this COTS constraint, the fact that we're trying to use sort of well-established, sustainable supply chains, but we're still not building systems that are good at sort of staying alive in space. The more that we can focus funding and attention and awareness globally on building out these systems, the better our systems are going to be and the longer they are going to last on Earth. There is no reason why we shouldn't be building with these constraints in mind. Even if you don't do space work, it's a great fitness function. So my last thought, because I enjoyed giving a little talk on the kernel in space. And again, if you want a highly technical version of this, I'll be giving it in about 2 months. But I really like working in and around open source. I have my entire career. And I do that because it allows me to work with some of the smartest people on Earth, and I never know who it is that I'm going to work with next. I just find the problem, the technical problem, I type it into GitHub, I see if anyone has been trying to solve that problem in their spare time, and then I reach out to them. That's how things like Gadfly got started, right? Working with a bunch of experts who are just willing to align and solve a really, really, really hard problem. Increasingly, and I will continue to be giving this talk on space because I want people to have this perspective. If you are contributing to open source, you are contributing your time. You could be doing anything else with that time. Make sure that your contributions are meaningful. Do not get wrapped up in this sort of everything has to be like built, sold, and sent off in an agile time period, and it all has to go to market in 2 years, or it doesn't matter. There are a lot of people still working in open source that focus exclusively on long-tailed solutions, long-tailed problems. The more that I can get people to continue working on that, the more that we're going to see more sustainable solutions, because you're not just going to go work on a repo for 2 years and dump it because you didn't get enough GitHub stars. I want you to focus on solving problems that are deeply, deeply meaningful. And you can do that. Again, KubeStat, there's a couple of other ones, but if you go and contribute 5 or 6 meaningful commits to KubeStat, your intellectual property, the work that you did with your hands on a keyboard, will go to space. And I think that's cool. So here's what we learned today. A little bit about the history of space, the kernel and the kernel in space. I hope you understand a little bit more about why we need to do the type of error detection, the fault tolerance and isolation, and the communication protocols, which we mostly skipped. But if you're interested in them, I can send you more resources. And a little bit about how these massive systems, right? There's other systems other than space, which sit outside of open source but strongly constrain it. Pay attention to them. So, as we return to orbit, thank you so much for joining me on this little gadfly romp. A couple of notes. I really enjoyed the UNICEF talk right before this. Gadfly does put out an open source zine called Cyberscape. And here's an example of some of the work. This is available on our website, but we have been reaching out and getting technologists from different regions of Africa to talk about their experiences of getting online. This is our very first Cyberscape zine. Again, no marketing, but if I find an artist who likes to do supply chain vulnerability art, you know I'm going to make a zine. This is the Log4j, Log4Shell versus another equally vulnerable system. And you can see that Log4j, Log4Shell, oh my gosh, whew. Well, I'm awake now. How about y'all? Turns out there's an edge on that. Thank you. It's my open source Jennifer Lawrence moment. All right, so here's what this art shows you, and I think it's so cool. So it's an equally dangerous, equally vulnerable vulnerability, but why do these have different colors? One shows that this one was basically ignored, this one was dealt with, and what it shows you is that we are communicating vulnerability management statistically best by Twitter. It shows you that the vulnerability of Log4j was solved mostly by the vectors of Twitter, and not from any of our supply chain management services that we pay for. Concerning. A last note, Gadfly AI, where can you see us hanging out next? So I did just submit to be one of the independent board advisors for OSI. If you think that this stuff is interesting, you should check out all the AI and cybersecurity work that I do. If you want a better version of this talk in which several maintainers get up and talk about hardware and software in space, you can see that recorded talk at Open Source Summit in just a couple of months in April. And we are doing a live art show around cybersecurity and the supply chain at Linux Fest Northwest as well. And maybe I will see you there. That is just about it. Thank you so much.
Are you okay? And tell me, it was, of course, scheduled. It was fake. No,
I hope you're not in pain.
All right. So, that's the gong. Don't go.
Saul.
Yeah.
Here.
Oh, God, I'm back. Yeah.
Yeah, we have 2 minutes for a Q&A. And, of course, the trophy, Shrodi. Well deserved, I must say. Well deserved.
Yeah, really interesting
Yeah,
talk.
I'll throw this back on. I will say it's the first time I've given that talk. It's just a hobby space for me, but honestly, any questions around the topic, I will take and probably turn into a blog post. So if you've got a question that I can't answer, I will work on it because I find the space fascinating. But any questions at the moment as I recover from falling?
All right, so questions?
Cool.
Don't be shy. You are smiling, so you want to ask a question. No? You're saying no? Maybe it's true, maybe it's not. All right. No one? Because I have some.
Okay.
Oh.
You mentioned one way for people to maybe, I mean, you're at a very high level in this space. You mentioned CubeSat. Can you expand more? on
Yeah,
that?
so for the next talk that I give of this, oh dear, for the next talk that I give of this, I will be providing a whole list of open source things that I would really recommend contributing to. But the one that stood out to me, CubeSat. So that when I look at recommendations that I would make, like, is there a barrier to entry? Is there an external culture to the GitHub repository, for example? Some of these, like the protocols, you probably can't engage with unless you have a PhD understanding. Great, I won't touch those. CubeSat, if you've got a Python level understanding of mathematics, you can be contributing to that. Yeah, that has a direct relationship. It will be released into space technology. Yeah.
I have a question. Is there any documented case of a vulnerability that has happened in space?
Yeah. Yeah, so it's interesting. So it's one of the most isolated environments, right? So you'll tend, if you're working in a highly secure environment, right, military space environments, these are completely isolated environments. When it gets interesting is kind of making sure, so they'll tend to send out patches, right? So they do patches in the same way that sort of get like bounced along satellites till they get to their end route. So they do patches in exactly the same way that we all do patches, right? Can I say that Log4j and Log4Shell was implemented in it? I honestly don't know, but if I had to put money on it, I would bet money that Log4j, Log4Shell was patched, right? But the thing that you have to understand, how do these things work, right? When you've got any of these would have been informed before the general public. So before the general public is informed on a 0 day, you receive the 0 day because they now think that like it's been tightened down for many of the critical services, right? So think about your like water systems run on Kubernetes, that kind of stuff. All of that stuff has been patched and cleared before a public 0 day is announced. So their patches are done. So yeah, don't bother going and trying to like black hat, they're already patched, so.
Imagine be at home and receive a phone call. Sir, you just broke production. Your son?
Yeah.
Not the best call.
Yeah, but I mean, they're beautifully redundant systems. They're always like minimal Linux kernels, and so they're the most robust things you can look at to study. So.
Mm-hmm. Any other questions, guys?
Oh, all right.
Cool.
So I see no other hands up in the air. So we can
Cool.
give another round of applause to Sal.